What is voltage? Well, I like to compare this to something we already learned about, yes? Okay, I want to compare this to gravitational potential energy. So, a little blast from the past. First we will look at this, and then we'll come back and answer that voltage question. So, blast from the past. Let's say we have a big mass, maybe it's a planet, and then we have a little mass, m. And we know that those two masses attract each other. If we wanted to find the attraction between those two, we could use that formula F equals G m1 m2 all over r squared. That's Newton's law of gravity, which is very similar to Coulomb's law of electrostatic charge. And many people go to workout gyms and they take advantage of this attracting force. They use it to work out their muscles. And basically, if you want to lift this little mass up, okay, you're going to have to fight this attracting force. So all the way as you lift that up, oh my goodness, yes, you're going to be fighting the attraction it has to the bigger mass. Therefore, since you're going to have to be exerting an upward force through that distance, you're going to be doing work the whole time as you lift that mass up. Oh, yes? And then once that mass is up here, what does it now have up there that it didn't have down at the bottom, Julie? Potential energy due to gravity. Now that it's up here, it has so much potential energy due to gravity, yes? And if I did 100 joules of work to lift that mass up, then how much potential energy does it have up there on the top? Ricky? 100 joules of work. How much potential energy does it have up there now? 100 joules potential energy. However much work you have to do to raise the object to that altitude, that's how much potential energy it has. And then if you drop that mass, as it loses altitude, it's going to lose its potential energy. But what kind of energy would it be gaining? Let's go to the back. Ariane, as it drops down. Kinetic energy. And if all of the potential energy turns into kinetic energy, how much kinetic energy would it have, Diana, right before it hits the bottom?
100.
That's what I'm talking about. 100 what?
Joules.
100 joules, yes? So this is what we did in the past. Now we're going to do the same exact thing all over again, but instead of taking advantage of the attraction between two masses, we're going to take advantage of the attraction between oppositely charged objects. You all ready for this? Let's say we have a massive negatively charged object. And on top of it, let's say we have a positively charged object. Perhaps they're insulators, so they don't immediately ground each other out. We know that these two objects attract each other as well. If we wanted to calculate the attraction now, Coulomb's law of electrostatics. K Q1 Q2 over R squared. We could use this attraction force to work out our muscles. This time you go in, you grab that positive charge, you lift it up. All right, and you bring it up to here. And once again, that would not be easy. You would be fighting the electrostatic attraction force between the charges. Since you're fighting that attraction forces, once again, on the way up, you would be doing work. Let's say this time you did 200 joules of work. Well, guess what the charge up here has now that you've done work and you raised it up farther away from the negative charge? What do you think, Bradley? What is it going to have up here that it didn't have down there?
200 joules.
What kind of energy? Well, what kind of energy did it have in the last time up there?
Gravitational potential energy.
Gravitational potential energy, yes. So this time, it's going to have
potential energy due to electric forces.
potential energy due to electric forces, exactly. Or sometimes it's called electrical potential energy. So now that you raise that charge up here, it's going to have potential energy, not due to gravity, but due to the electrical field, the electrical attraction between the two. And how much potential energy will it have up there, for Jacques?
200 joules.
That's what I'm talking about. You answered my question, now let me answer yours.
When it's on the ground there, the
Yeah.
radius would be 0, right?
What's that?
The radius for the equation, because there's really no distance between
No, remember the radius is always from the center of one object
them. Oh.
to the center of the other object. So if we were doing something like back with gravity, if this was the Earth, sorry Earth, and you were standing on top of the Earth right there, okay, then what's the distance between those two objects?
Oh, from the center of the Earth to the center of the Earth.
And basically what would it come down to? What would it essentially be?
Just like the radius of the Earth.
The radius of the Earth, exactly. Okay. Once again, I do work to lift that positive charge up. so tired, man. Yes? And now that I have it raised up to here, you know, you ever see those people at the gym, you know, they raise the weight up and then they're like all hot shots, so then they just drop it into that floor, which could take the pounding, yes? You ever see that?
Yeah.
Well, let's say we just drop the positive charge, you know, and it goes flying down, yes? Once again, it's going to be losing its electrical potential energy. But what do you think it'll be gaining, Mike?
Kinetic.
That's what I'm talking about. And how much kinetic energy?
200 joules.
That's what I'm talking about. So it's a very similar system where the work done is equal to the potential energy at one location is equal to the kinetic energy at another location. Here's the difference. For some reason, when you're dealing with electricity, it is more common to talk about the work per charge and the potential energy per charge and the kinetic energy per charge. Instead of talking about the whole work done, it's more convenient to talk about the work done per charge. So, watch. Let's say that this little positive charge right here, I'm going to call it Q2, because the big papa one down here is Q1. Yes? Let's say Q2 is equal to positive 2 coulombs. Yes? Now, when that charge was lifted up, yes, 200 joules of work was done to lift the whole thing up, which was 2 coulombs. Well, how much work then was done to raise each of the coulombs? How much work was done to raise each of the coulombs? Jessica? 100 joules per coulomb, exactly. Okay, so the work done per charge is equal to 100 joules per coulomb. Yeah. Hey, what was the total work done? Well, I did 200 joules. Wow, you did a lot of total work. Oh, what was the work done per charge? 100 joules per coulomb. This is more common than that. Anyone want to take a guess what work per charge, joules per coulomb, is actually equal to? Anna. Voltage. Yes. So basically, the voltage is 100 joules per coulomb. Voltage is just another name for work per charge. When you see that word voltage, don't be afraid. Just think, oh, it's not the total work. It's the work done per charge. And then to honor Alessandro Voltas, Italian physicist, guess what a joule per coulomb is also called?
A volt.
A volt. So we could say that the voltage is 100 volts. This is the first time the symbol used in the formula, hello capital V, is the same as the symbol used for the unit. You follow what I'm saying? Like, look, usually, like, if we have force equals 5 newtons, yes? Look, the symbol for the units, N for newtons, the symbol for the force, capital F. F and N are not the same letter, yes? This is the first time the symbol used in the formula is the same as the symbol for the units. So, it's so easy to forget what a volt is. So we'll play a little game. I say volt, you say joule per coulomb. Volt.
Joule per coulomb.
Volt.
Joule per coulomb.
I say volt, you say joule per coulomb. Volt.
Joule per coulomb.
Volt.
Joule per coulomb.
Okay?
They say that.
It's like the Color War song, I say go.
There you go.
You're just like the crescendo and super. It's like,
Now, if we wanted to write it as a formula, electric voltage is equal to the total work done divided by the amount of charge that the work was done on. What also adds to the confusion a little bit is there's like 3 different names for the V. Of course, it's known as voltage, but it's also known as electric potential. Not electric potential energy, electric potential. Or, wait, there's more. Sometimes it's called potential difference.
Like those are the same thing.
Those 3 are all synonymous. Spell check.
No, really?
Synonymous or synonymous?
Synonymous.
There's two of them.
Yeah, you got it. If it's wrong, I'm telling the board. I'm telling the superintendent if it's wrong.
There's no way you can put this online.
Okay.
Oh, whoops. Yup, that's how you spell it.
But remember we were just saying a moment ago how the work done to raise that charge up is equal to the electrical potential energy at the top point, which would be equal to the kinetic energy of the object at the bottom point. Well, if those three thingamajigs are equal to each other, conservation of energy, then when we define voltage as work per charge, guess what else voltage is actually equal to? Potential energy per charge. What could be another formula for voltage? Kinetic energy per charge. So let's try to connect this to something that you could relate to. You all ready for this? Let's say we have a standard D battery, drawing it a little bit bigger, of course. Size D. Those bigger batteries, you put in a flashlight, yes?
Does the letter have to do with voltage or just like the size?
Just has to do with the size. Turns out that AA, AAA, C batteries, D batteries, those are all 1.5 volts. Okay, so 1.5 volts. Now, I'm sure you were exposed to this in chemistry, but inside of a battery, there's like some sort of acid, yes? Like acid. Yes?
My mom told me that sour Skittles are like battery acid.
It's true.
Really?
Probably.
They are? But that's my favorite candy.
It's a drug. It'd be dangerous.
Now, in this acid, there are two pieces of metal, different substances, that are dipped into the metal. So here we have one metal that's dipped into that acid. That particular piece of metal sticks out the end of the battery a little bit. And then over here we have another piece of metal where its end is kind of flush with the battery. That also goes into the acid, yes? So down here we have acid. Okay? And then we have two blue pieces of metal there, yes? Now, when this piece of metal here reacts with the acid, yeah? That particular chemical reaction uses up electrons off of that piece of metal. So as it's reacting with the acid, electrons are constantly being sucked off the piece of metal and used up in the chemical reaction. So if electrons are constantly being taken off of there, yes, what kind of charge is going to be left on that particular piece of metal? Say it loud, say it proud, Samantha.
Positive?
Are you positive?
Yes, I'm not.
No,
I'm neutral.
you're neutral.
Yeah. Positive.
You have the same number of protons and electrons. You're overall neutral. Okay. Okay. Meanwhile, the other piece of metal is having a different chemical reaction over here, and this chemical reaction is producing extra electrons. And as the reaction continues, more extra electrons are produced on this particular. So the piece of metal that is so lacking electrons, this one over here, imagine somebody who's like parched for water, like, oh, I need water. Well, this thing's parched for electrons. Oh, I need electrons. Yes? This one over here is like somebody with their, mouth completely filled up. So if you take this now and you connect a wire, a metal conductor, to a light bulb, now what actually flows through the wire? Electrons. The electrons in a metal conductor can jump from atom to atom. Yes? So check out how this happens. Let's say there's a free to move electron right here in the wire, right there, yes? Okay? How is that electron going to feel about all the electrons over here on that piece of metal with all the extra electrons? Get away! Yeah, 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 yeah! So it's going to flow this way, yes? So the electrons are going to flow this way. They're going to go through the light bulb. As they go through the light bulb, they have collisions with atoms, excite other electrons into higher energy levels. When they drop back down, guess what's released? Light. But that same electron continues on its path through here, through there. Yes? Continues that way. And as it comes back over here, how is that electron going to feel about this positive charge over here? Hey, how you doing? Yes? Going to be attracted there. You follow me, people? Now, let's compare that with this next diagram. See if you can follow me. It's on this next diagram. Okay? If I took that electron and I put it in between these oppositely charged objects, yes? Let's say I put the electron right in here. Which way would that electron naturally move? Right away, Prashant.
Oh, sorry, I'm sorry. Down. I was looking at the marker, I thought it was positive.
Oh, sorry about that.
Yeah.
I hate the marker always stays there. I know. Sorry about that. Okay, so if it's negative, it's going to immediately go down, yes? So it's going to go down, here. Now, let's say I don't want that electron to stay down there, yes? Okay? What am I going to do? I'm going to go in there somehow or another, and I'm going to lift that electron up, and I'm going to push it up towards that other negative plate. Come on, electron. Oh, man. You know, resistance is futile. Anyone know where that line is from? Resistance is futile. I think it's from Star Trek. Yeah.
Oh,
Resistance is futile. All right. So, ladies and gentlemen, since I had to do work to lift that electron up here, guess what that electron is going to have at that higher position? Electrical potential energy.
P.
That's P. That's a lot of P.
Oh wow, I just got that.
It does. Oh, back to work, yeah.
So, ladies and gentlemen, we were just talking about how if you raise that electron up, it wouldn't naturally go up there. That would take a lot of work, yes? Okay? And then when it's up here, it would have so much electrical potential energy. Follow what I'm saying, people? Okay. Well, now, let's go back to the battery situation here, yes? Now, this electron in the wire right there, does it naturally want to stay right there next to the negative terminal? No. Okay? It's kind of like this electron here right against this negative terminal. So basically, when the electron is right here, guess what it has? Guess what it has a lot of?
Potential energy.
A lot of stored up electrical potential energy. Yes? A lot of stored up energy. A lot of electrical potential energy. And basically, as it goes through the wire, that electrical potential energy is turned into light energy. And when it gets back here, guess how much electrical potential energy it has? Zero. Okay? So right here, the electron has a lot of PE. But after it goes through, back to here, at that point right there, now, in order to get that electron back from the positive terminal, because that's where it's going to go into, woo! Yes? In order to get it back from the positive terminal, back to that negative terminal, that's not going to be easy. The electron's not going to want to leave the positive terminal. Hey, how you doing, positive? I like you, positive, yes? It's not going to want to go back to those negatives. Oh my God, it's so crowded over there. Oh, yes? So what is it going to take a lot of to get that electron back over there? A lot of work. Nicely said. A lot of work. It would take a lot of work to get that sucker back over there, yes? And basically, the battery being 1.5 volts, that tells us how much work the battery is going to do via its chemical reaction to get the electron back up on that negative terminal. Since it's a 1.5 volt battery, that means it's going to do 1.5 joules of work to move each coulomb of charge from that positive to negative terminal. Now, of course, the electron is not a coulomb of charge. The electron is much, much smaller than a whole coulomb. But nonetheless, this is an indication of how much work it would take to move that electron back. Samantha?
So like what makes a battery like run out of like batteries?
Well, just like all chemical reactions, you have so much stuff to begin with, yes? And if you take this chemical and you take that chemical and you put them together, there's a chemical reaction, and then the original stuff turns into products, yes? Well, with all chemical reactions, eventually you run out of original stuff. You follow what I'm saying? And when you run out of original stuff, the chemical reaction is over. And all batteries basically run out of stuff.
Like
Okay?
acid?
Not the acid itself, but like usually what happens and I could be wrong, I don't remember which one is which, but usually like one of the metals, as the chemical reaction goes on and on, guess what happens to the amount of that particular one?
Or decreases?
Yeah, it decreases. You know, it starts to like, go down, so it starts to, look like, like this, and guess what happens to this guy over here? Yeah, it gets like, a coating of, some kind of plating on it, yes? And eventually you're going to run out of one of the metals. And once it runs out, there's no more like chemical reaction to be done, so it has no means of moving that electron back over. How is that electron moved back over? By the chemical reactions. Yes?
How do you charge for batteries?
Well, do you remember from chemistry that some chemical reactions are reversible? Yes? Well, a reversible chemical reaction has to be used, which forces the natural occurring chemical reaction to go in reverse. So the electrons, which normally in the normal chemical reaction are put from here to here, well, you have to force the electrons to go the opposite way. And when you plug in a battery into a charger, it basically forces the electrons to go in the opposite direction, making the reverse chemical reaction occur. And basically you would be building this back up, and this would be like back, dwindling back down. You have to have a reversible chemical reaction. I don't know if that helped you a little. So let's figure out how much work does this battery do to actually bring that electron over there from the positive to negative. Yeah,
What's the highest voltage battery?
that's a good question. That's a good question.
Like car batteries.
I know like wall outlets, you know how there's two little slots?
Yeah.
Okay, inside one slot, there's a piece of metal that's, for the moment, positively charged, and inside the other slot, there's a piece of metal that's negatively charged, and the potential difference, or the voltage between those two, is 120 volts. Okay, a standard car battery, I think, is like 12 volts. I don't know how high the batteries go. I'll have to look that up. How much work does the battery do to bring one electron from the positive terminal to the negative terminal inside the battery by means of the chemical reactions.
So like, are you talking like almost flowing through the acid?
Yeah, because through the chemical reaction, electrons are used up over there, and then they're put on that one over there to keep this guy over here negatively charged and keep that plate over there positively charged.
So acid isn't conductive.
Yeah, so acid, somehow or another, like, you know, I'm thinking of like SO4 to the negative something or another, or, somehow carries that over. So how much work does the battery do to bring one electron from the positive terminal to the negative terminal inside the battery? Well, once we know the voltage, we know how much work it takes to move any quantity of charge. If I rearrange this formula for W, what does W equal in terms of the other two variables? Samantha. And basically, this particular battery is how many volts, Bradley? 1.5 volts. And the charge, okay, is 1 elementary unit, because it's 1 electron. It's actually -1.
You have to convert that to cool.
Yes. 1.5 volts, so I say volts, you say. It tells you how many joules it takes to move a whole coulomb. That's like a big monster gang of charges, yes? But an elementary unit of charge, the charge of an electron, that's way, way smaller. Anyone remember that conversion? Rami? Excellent memory.
We're supposed to memorize that?
No, you would be given that. But if you use it enough, it sticks with you. So the electron is a small, tiny little piece of the big coulomb. How much work does it take? Oh, 1.5 joules of work per each coulomb. And if you multiply that out, what do you end up getting? Little help? Robbie? And don't worry about the negative sign there now. Eventually we'll talk more about the positive and negative sign on the work. So to move one single electron takes a tiny, tiny amount of work. But if you're moving massive gangs of them, okay, for each big gang of them, each coulomb, it would take 1.5 joules. Question? So, here's another battery.
Like a 9 volt.
I was thinking more like a car battery, but it could be like a 9-volt battery. So voltage, also known as potential difference, also known as electric potential, all of these are equal to the amount of work done per charge to move a charge from one place to another. Now here's the thing. If I imagine moving an electron from here over to there, okay? If I was going to move an electron from there over to there, it would definitely take work, yes? Okay? It would definitely take work. That electron wouldn't want to go over there. But what would happen if... Bless you! Bless you. What would happen if I made this sucker over here even more negative, and this one here even more positive? Yes? Now, to move that sucker over there would even take more work per charge. You follow me? So, the way I like to think about it, anytime you're talking about the difference between one point, say point A, and another point, point B, and you're talking about the voltage between those 2 points, or the potential difference between those 2 points, I always think of it this way. Well, the greater the voltage between those 2 points, the greater the difference in electron concentration. In other words, this one is even having, a higher concentration of electrons. This one is even having a higher lack of electrons. So, I sometimes like to think of voltage as an indicator Yeah.
Is that the greater the difference, the greater
The voltage. So, for example, if you had this battery that had, a little bit of extra electrons on this terminal, and a little bit lacking electrons on that terminal, and then you had another battery that had a higher concentration of electrons over here and a higher lack of electrons over here. Okay. I wanted to show a huge difference. Basically, which battery is going to have a higher voltage? Julie? Yeah, the bottom one. Okay, so this one here is going to have a higher voltage. This one here would have a lower voltage. This one down here, it would take more work to move an electron that way. Okay? Okay, this one here, it wouldn't take as much. in closing of this part of the lesson, let's just go over the formula for voltage, the units for voltage, and alternate names for voltage. Okay? So Risa, start us off with the formula. Voltage is equal to work over charge. It's not the total work, it's the work per charge. Okay? What are the units? Riki? Volts? Or joules per coulomb? Alternate names? Vishak?
Electrical potential. Potential difference.
That's
Why did
okay.
you say alternate